Hello, and thank you for joining us for our second video on shear turbulence. In this particular video, we're going to continue talking about the theory of shear turbulence, and specifically, we're going to look at different conceptual models. So, shear turbulence can be thought of as either two things, and actually one leads to the other. That would be breaking waves or eddies. With the breaking wave, wind shear produces a wave as a result of the viscosity of the molecules. Molecules of air are trying to stick to each other and trying to overturn each other. As a result, a wave develops. And this wave may reach a critical value, a critical amplitude, where it will break on itself, just like a wave on the shore breaks. And the resulting eddies are what produce the turbulence. Here is a video that shows shear inducing a wave that breaks and produces vortices and turbulence. Another way that shear turbulence can be generated is simply bypassing the wave mode of the turbulence and going straight to the eddy. In other words, no wave develops, it's just the shear is strong enough that induces eddies that break down. Normally, the airflow starts out as being laminar as it moves over the ground or other surfaces. Then it starts to transition into a turbulent mode based upon the stability of the atmosphere and the shear that is also in the atmosphere. These eddies propagate downwind. These are what cause gusty conditions over an anemometer at an airport. So to get either of these, either the eddies or the wave, two things are required. Of course, you need wind shear, and in the previous video, we talked about the definition of wind shear. But also, you need a certain amount of stability in the atmosphere. So the wind shear can be horizontal, vertical, it could be directional, a change in direction or a change in speed. In this picture, you can see vertical shear in the magnitude of the wind, but you can also have directional shear, and as I mentioned, this can also happen in the horizontal. And as I mentioned before, with shear, the wind at a higher level is moving faster and a lower level moving slower. It could be reversed. You can have slower moving wind at a higher altitude and a faster moving wind at a lower altitude. But regardless, you have the viscosity. What viscosity is the ability for molecules to stick to one another. You can think of it almost kind of like friction between the air molecules themselves. One wants to stick to the other. And at that interface, if one that is moving faster sticks to one that is moving slower, you can see how the air will overturn. And that's what we saw in that video. Another thing that you need for shear turbulence is a certain amount of stability in the atmosphere. The stability will suppress turbulence. In other words, it will prevent turbulence from forming until the shear becomes so great that it overcomes the stability. Another thing that the stability does is that it suppresses convective mixing. Convective mixing are thermals rising through the atmosphere and compensating motions sinking down through the atmosphere. When that happens, it mixes the atmosphere out. It takes stronger winds and brings them down to the surface. It takes weaker winds at the surface and brings them aloft. So in other words, it reduces the magnitude of the shear. You see this just about every day if you're out the airport for extended periods of time. You notice that at night and the early morning hours, the winds are very light, but in the afternoon, the winds will become stronger. The reason is because of this mixing. When the sun sets, the air becomes more stable and the atmosphere starts to decouple. Meteorologists call this decoupling, where the winds at the surface decrease in strength, but they actually do increase in strength a few hundred or even thousands of feet above the ground. So there is a point where you need to have a certain amount of shear for a certain amount of stability to overcome the stability and to create turbulence. We call this shear value the critical shear value. It's the amount of shear that's required to produce turbulence. If the atmosphere is very stable and you have a certain amount of shear, you won't get turbulence. But if the air is unstable and you have the same amount of shear, you can get turbulence. So it depends upon the stability and the shear. They go hand in hand. A good way of examining this is to use an analogy. And I call this one the dike and dam analogy. So we're looking at Grand Forks back in 1997. That was many years ago, but there was a devastating flood in Grand Forks. And at that time we had a very small dike down on the river to prevent the mighty Red River of the North to overflow its banks. So in 1997, there was not a very big dike, and the water did overcome the dike and flooded the town. But the flooding was not devastating. People were not killed. People were able to get out of town in time. However, there is a new dike, and it is massive, and it's able to hold a lot of water behind the dike and keep the river within its banks. But there will come a time when we have so much snow and so much rainfall that the water will overcome the dike, and the consequences of flooding in town will be devastating. So this is a lot like the stability and the shear in the atmosphere. Stability is constantly trying to hold back the shear to prevent turbulence. But there will come a point where the shear becomes so strong it will overcome the stability. If the stability is so large, you need a very large amount or huge amount of shear to cause turbulence, and the turbulence will be severe. If the stability is weak, then you need a small amount of shear to overcome the stability, and typically with low shear values you're going to have just light turbulence. This was first recognized by a professor named Lewis Fry Richardson back in the 1920s and 1930s. He came up with a concept of a balance between stability and shear, and we call this the Richardson number. So Richardson numbers are typically small for shear turbulence because that means you have big shear or small stability. Let's go back to our video of the wave that developed as a result of shear. Before, we didn't look at the stability of the atmosphere. Let's add some stability now, so that on the top, in the white area, you have less dense fluid, and in the bottom you have more dense. This is the case. More dense fluid tends to stay low, and less dense tends to stay high. So this is a stable situation. You have stability, and then you also have shear. And because of that stability and shear, you get a wave that develops and breaks and produces very strong turbulence. That's the end of our second video on conceptual models. After this, the third video, we'll get into the different locations where you can find shear turbulence.